Welcome. In this module, we will define network oversubscription and analyze why it is the primary bottleneck to avoid when designing high-performance, eye-training fabrics. Traditional networking, we often design for oversubscription connecting 40 servers to a switch that has only enough uplink capacity for 10. This 4:1 ratio works for web traffic because user activity is sporadic. However, eye-training is different. It generates massive sustained data streams called elephant flows. In this module, define oversubscription as the ratio of downlink bandwidth to uplink bandwidth and explain why high-performance eye demands a non-blocking, or 1:1 ratio to function effectively without choking data movement. This diagram illustrates the bottleneck. On the left, we see a traditional 3:1 or 4:1 oversubscribed network. Multiple servers try to push data through a single uplink, causing congestion and dropped packets. On the right, non-blocking 1:1 network provides an equal amount of uplink bandwidth for every bit of downlink bandwidth. This ensures that even if all servers transmit simultaneously, which happens constantly in AI, the network can handle the full load without restriction. Is this ratio so critical? AI models use collective operations like all-to-all or all-reduce, where every GPU must talk to every other GPU simultaneously. If you have a 2:1 oversubscription, you effectively cut your training bandwidth in half. Unlike web browsing, where a millisecond delay is unnoticed, AI training is a tightly coupled process. A reduction in bandwidth directly prolongs the training iteration, making the entire job and reducing the efficiency of your expensive GPUs. Here we visualize the impact of the traffic jam. In the top scenario, we have a 1:1 ratio. The data flow moves from the GPU cluster to the network switch and out to the destination at full speed, 400 Gbps. In the bottom scenario, an oversubscribed link creates a bottleneck. The switch buffer fills up because the ingress is faster than the egress, leading to congestion, throttling, and reduced throughput for the critical gradient updates. Ultimate penalty of oversubscription is tail latency. In distributed AI training, the entire cluster waits for the slowest node to finish its update before moving to the next step. If oversubscription causes congestion for just one packet, the tail thousands of expensive GPUs sit idle, wasting power and time. This idle time compounds over millions of iterations, significantly increasing job completion time, JCT, and reducing the return on your infrastructure investment. This Gantt chart compares two training iterations. The top bar 1:1 network shows a compute phase followed by a short, predictable communication phase. The bottom bar, oversubscribed, shows the same compute phase, but the communication phase is dragged out due to network congestion and tail latency. Red idle wait blocks represent wasted time where the expensive GPUs are doing nothing but waiting for the network to catch up. To eliminate oversubscription, we use a design called rail-optimized topology. Instead of a generic mesh, we build dedicated parallel networks or rails for each GPU position. For example, all GPU zeros across the cluster communicate on rail 1 and all GPU 1s on rail 2. This ensures a fully non-blocking 1:1 fabric that maximizes the performance of operations like all-reduce, keeping your eye training running at the speed of light. This diagram maps out a rail-optimized topology. You see two servers, server A and server B. Instead of sharing one big pipe, GPU 0 in both servers connects exclusively to the rail 1 switch. Simultaneously, GPU 1 in both servers connects to the rail 2 switch. These parallel, isolated paths ensure there is zero contention between the rails, providing a true non-blocking fabric for massive all-to-all communication.